welcome everybody on board this first webinar from the consortium of the FCH-JU project Hypactor. You will have today a short overview of our activities. This project is on its way. We will finish the project on next June due to an extension of 3 months of the project, which was first due to end at end of March next year. So we will end the project in June 2017. Okay. So first overview of the project. I will go through a few items during my talk, short talk, to leave some availabilities from the technical presentation also. So I will talk about the current challenges who push us toward the proposal of Hypactor project to the FCH-JU. Then I will present you the Hypactor consortium and project structure. I will talk, my partners will talk about the activities, the technical and dissemination activities of the project. We will show particularly some preliminary results. And we will end the presentation with some dissemination and perspectives. And to close this webinar, of course, we will have a special time for question and answer session. And so, as Philippe says at the introduction of the webinar, you could write your question during the webinar using the chat mode of the webinar. Okay, so don't hesitate to ask any question you have, and we will try to answer them at the end of the talk. Or if not, if we don't have enough time, you can of course reach us by email after the webinar is finished. Okay, so about the challenges, most of you certainly know that hydrogen is expected to be a highly valuable energy carrier for the 21st century. We all are convinced that demonstrating the optimum safety in use is essential and will contribute certainly to help its social acceptance and also broaden its use as an energy vector. We also know that the feedback that is currently gathered on cylinders in service are mainly from metallic cylinders, fully or partly metallic cylinders. And we know from the real-life example that the resistance to mechanical impact is of main concern. The Hypactor project is one of the first of this kind and aims at strengthening the knowledge on the influence of mechanical impact with respect to type 4 composite overwrap pressure vessel integrity.
La diffusion vient de démarrer. Tous les participants sont en mode écoute seul.
Okay, that's a kind message. So this is a few pictures about what we think when we say about when we talk about real-life example. That could be from truck rollover or fall down. That could be hit of some cylinders which were mounted on the roof of some buses or trucks that go through bridges where they should not have gone. There are also road incidents. There are also rollover which could also be also coupled with some fire issues, or there could be at the end also at last some let's say attacks from aggressive people, let's say. The consortium now, so it's composed of 7 different partners, 4 from France. CA is coordinating, Air Liquide, Aiming, and Institut-JU. We also got partner from Poland, the Wroclaw University of Technology, and 2 partners from Norway, the Norwegian Technical University from Trondheim, and we also have Hexagon Composite with its third-party Hexagon Lincoln in the US. Okay, brief overview of the competencies or the contribution of each partner in the project. So composite pressure vessel testing, it's mainly CA and VUT. Companies operating CPV, Air Liquide and Hexagon. Tank supplier Hexagon. In this project we are only testing cylinders that are all manufactured by Hexagon on a serial production line. We have partners for non-destructive testing development, which is Institut-JU, VUT and CA. Modeling, for the Norwegian university. Regulation code and standard development, Hexagon, Air Liquide, Institut Studio, and CA, and project coordination team or support to the coordinator aiming. About the organization, the concept of the project. So we start from the fact, from the experimental work on the mechanical impact and damage. When we have subjected the tanks to impact damage, then we assess their residual performance, both for short-term and long-term. In parallel, of course, we perform some non-destructive examination methods to characterize the damage, but also to contribute to the definition of pass-fail criteria for the regulation code standards. And we do most of the testing on reference cylinder, which is 36-liter cylinder with service pressure at 70 megapascal, 700 bar. But we also have included in the project some validation on some larger cylinders with various service pressure. So talking just about the work package organization or work package structure. So coordination, work package 1, 3 big technical work package. One from the study of damage due to impact, work package 2. Then work package 3, the assessment of the residual performance of these impacted tanks. In parallel, the inspection method developments. And finally, a work package dedicated to the dissemination and the recommendations toward normative committees. About the goals, one of the first big goals of the project is to aggregate an extensive experimental database which link the impacts, characteristics, and the damage to the tanks and the residual performance. Then, of course, we want to achieve in a deep understanding of the relationship between impact, damage, and loss of performance of the cylinders. We want to be able to develop some modeling to be able to simulate or extrapolate the mechanical impact on CPV and their residual performance. Then we want to assess and develop relevant non-destructive testing for inspection procedures. And of course, as it is a pre-normative research project, we aim at being able to provide recommendations for the committees. And it's our main concern is focused on qualification requirements and acceptance criteria for new designs. But we also want to propose some enhanced maybe impact test configuration or some procedures for periodic inspection. That is all of our purpose for this research project. Few words about the application that are targeting in the project. So we assess stationary buffers. We assess transportable monocylinders. Cylinders which are mounted in transportable bundles, or even the permanently mounted cylinders for trails. Few words about the testing activities, just to provide you a first overview, and you will have a detailed presentation in the next talk. So an average figure about the tank that were tested in the project. So it's an average number of 100 tanks, different tanks tested in the project, from service pressure from 250 bar up to 950 bar. Water volumes from 36 liter up to more than 500 liter. We tested different impact energy from low energy up to 10 kilojoule. Impact weight from 1 up to 100 kilograms, speeds from 3 to 120 meters per second. Multiple impacts, various pressure of the cylinder submitted to impacts up to the maximum allowable service pressure. Test to failure or test impact just for characterization. And we have assessed the residual performance, talking about short-term, but also long-term evaluation. Okay, that's all for the introduction. I will now give the computer to Olivier. We will directly move for a more comprehensive, let's say, introduction of the project. We will move directly to the work package 4 to talk about the inspection methods.
Thank you, Fabien. Olivier Bardou from Air Liquide. And let's talk about inspection methods, work package 4. What are the objectives of the work package 4? First, to define the non-destructive technique protocols to be used in the other work package to assess, to have the characterization of damages. Second, to define a pass-fail criteria for visual examination and acoustic emission test. And then to give some recommendation for inspection procedures suitable with your operating constraints in operation. What is the methodology followed? First, to have the industrial constraints for non-destructive testing in operation. That's to say, provide the operating condition to consider for the implementation of acoustic emission and visual inspection. Secondly, to define characterization NDT protocols just to be able to identify the best non-destructive techniques to characterize the damages in terms of type, shape, location. Third, to collect acoustic emission data. The goal is to provide a suitable acoustic emission procedure according to all partners' equipment, and then collect all acoustic emission data coming from the other work package. And finally, to develop and validate a pass-fail criteria by non-destructive testing. For this, we have to define the acoustic emission trial plan, and then to define a pass-fail criteria to be used in periodic inspection of composite overwrap pressure vessels. Concerning industrial constraints for non-destructive testing in operation, two methods, acoustic emission and visual examination, are studied. They are the most mature at the beginning of the project. Two possible operating conditions were defined. First, in an existing filling center, we have gas pressure source available at this location, and we have few perturbations of operation. The second possibility is in dedicated acoustic emission workshop. For sure, we have more perturbation of operation, but we have also more possibility to adapt a dedicated bench with acoustic emission procedure. Definition of characterization with NDT protocols. A list of potential non-destructive techniques has been established with expected performance, and those techniques are dispatched on different partners. You can see the potential non-destructive technique that we have checked in this project: infrared thermography, chirography, deflectometry, scanner 3D, computed tomography, and ultrasonic technique. The relevant identified techniques are, first, visual examination. It's difficult to calibrate, but it's for sure necessary at time of filling. Then ultrasonic testing and computed tomography scan are used when necessary, just to have a good precision on damage assessment. And then acoustic emission, because it's a huge part of the project to define acoustic emission criteria. I give the hand to Fethi. Philippe, can you open Fethi's microphone, please?
Thank you, Olivier. I will try to display my screen. So thank you, Olivier. Hello, everybody. My name is Fethi Damen. I'm from the Institut-JU. And in this presentation, I will try to give you in a few minutes, I hope, a clear overview of the work done in the acoustic emission part. So, as explained by Olivier, the aim of this project is to assess
Fethi,
and develop...
excuse me, we don't see your screen.
Yeah. You don't see your screen.
Maybe we can go on with my screen if it's easier.
Okay, wait.
Is it okay now?
No. Okay.
It's okay?
Yes, we can see your screen.
Yeah. So, as explained by Olivier, the aim of this project is to assess and develop a relevant periodic inspection procedure based on acoustic emission for transportable composite vessel. In this task, the contribution of the Institut-JU can be divided into three parts. The first one is to define acoustic emission protocol to be followed by CEA and the RUD, since they are in charge of carrying out all acoustic emission tests. The second part is to build with all partners the acoustic emission trial plan. And the third one is to collect all data and establish pass-fail criteria. So let's start with the acoustic emission protocol. So in this project, acoustic emission tests are performed by different partners using different acoustic emission system. For example, CEA has a Mistral system, while the RUD uses a Valence system. So some tests are in France and other in Poland. And in order to limit discrepancies and obtain relevant and comparable data, the acoustic emission protocol was defined in the beginning of this project. So this protocol describes acoustic emission implementation for hydraulic tests and details all the verification to be done before and after the pressure test, such as sensor position, pressure sequence, for example, and acquisition parameters. So the challenge here is the definition of acquisition parameters to get the same results in terms of Hertz number and amplitude using the two systems, Valence and Mistral. So you can see here in this slide that the acquisition parameter defined allow us to find similar results in terms of amplitude and Hertz number. We have a difference around 7%, which is, I think, very acceptable result. Okay. So for the acoustic emission trial plan, it was done following two steps. The first step, which is illustrated here in this synoptic, aims to evaluate the acoustic emission activity recorded in the case of healthy vessels to constitute a baseline that will be compared to activity of damaged vessels. Ideally, each vessel should be tested before and after impact to study the evolution of the acoustic emission activity due to damage. But in our case, it generates a complex trial plan. That's why the solution proposed here is to apply acoustic emission only to a few healthy vessels from different batches, of course. So if in the case of low dispersion, these data can be considered as a baseline of healthy vessels. So for the second steps, we have the second step here in this in the right synoptic. It explains that acoustic emission tests are performed just after impact and also after different cycling periods until burst. With this approach, the challenge is to define pass-fail criteria enabling the identification of structural damage compromising the burst pressure strength, And this identification must be possible whatever the periodicity of the control, and in particular regardless the time between the occurrence of damage and the acoustic emission inspection. So here we have many cycling periods, 5, for example, 50 cycle, 5,000 cycle, and 15,000 cycle. So an example of dispersion study is shown here. The dispersion was evaluated for 3 vessels from different batches at different cycling period. In this figure, we have in the black lines the result at 100 cycles, in blue lines at 5,000 cycle, and in red lines at 15,000 cycle. The parameter calculated here is the sum of events detected by all channel at each pressure hold for amplitude higher than 50 decibel. So 2 conclusions can be drawn here. The first one is that acoustic emission decreases with the number of cycles. It's quite similar after 5,000 and 15,000 cycles. Indicated that it could indicate that the state of the vessel in terms of damage has undergone non-evolution between these 2 cycling periods. The second conclusion is that dispersion is very low between the 3 vessels, whatever the cycling period you can see here. So this result is very important because it allows shortening the test matrix and validates the approach followed regarding the acoustic emission trial plan explained before. So at this stage of the project, about 70% of the campaign test was already done, and the data analysis is in progress. So you can see here various volume that has been studied. For example, we have the 36 liter, the 255 liter, and 513 liter. These vessels have different features in terms of thickness, size, service pressure, and here we used the number of sensors was defined in order to ensure a similar sensitivity of detection for all vessels. For example, for the 36 liter we used 8 sensors. For the 255 liter 20 sensors were used, and for the 513 liter we used 18 sensors. So let's move now to the pass-fail criteria. So these criteria must cover all these volume, and to establish these criteria, acoustic emission analysis will be based on the Appendix 7 of the French guideline for acoustic emission, which is recently approved by the French government in 2014, and it's the unique code which define acoustic emission procedure for periodic inspection of composite cylinder. So as you can see here, this table, we have many criteria. 8 criteria are calculated to define the category of the vessel. We can obtain 3 categories. So for category 1 and 2, the vessel can remain in service, but if the vessel is classified in category 3, then the vessel is rejected. So the approach followed by the Institute Sudur to build pass-fail criteria will be to rely on the solid reference, either to assess compliance of criteria thresholds or adjust them for transportable type 4 vessels. Okay, and to finish an additional NDT technique called modal acoustic emission. Has been involved recently by the Institute to the scope of Hypactor. This method is used for periodic inspection and testing of COPVs, and now is under ISO standard project in the draft international standard stage. We had in the Hypactor project the opportunity to check this method. That's why we undertaken the necessary action to involve this method to the scope of Hypactor regarding the approval of all partners, the approval of the European Commission, and also all investment to be done in order to explore this method. So at this stage of the project, many vessels have been controlled by this method, and calculation of criteria according to the ISO standard is in progress with the collaboration of the Digital Wave Corporation from USA. And due to the lack of experience in Europe on this topic, results from the Hypactor project will be used by the work group 15 to feed the understanding of modal acoustic emission on composite cylinder, and I think it may have a direct impact on the ISO document. So thank you for your attention. I will give the hand to Olivier to conclude.
Thank you, Feti. So this is the last slide for Work Package 4. Just to conclude and to speak about dissemination to normative activity. First, concerning the pass-fail criteria to be defined for critical damage, what is difficult is that we need accurate knowledge on critical damage, and then we will speak about it in especially Work Package 3. And this critical damage may be sensitive to cylinder type. Concerning visual inspection criteria, it has to be used properly at time of filling. Classical acoustic emission criteria are under construction, as Feti said. And concerning modal acoustic emission, the tests are in progress and analysis is also in progress. What is sure is that is a way to check the draft international standard 19016 and to try to give support to the working group 15 at the technical committee 58, and then to explore properly this method, this new method. Thank you for your attention. Just before switching to Work Package 2, I want to remind to all participants that if you have some questions, you can put them on the chat on the pop-up on the right of the screen, and the questions will be treated at the end of the webinar. Thank you.
Hello everyone, my name is Noémie Alexandre from the CEA, and at the end of the presentation, middle of the presentation, this presentation will be made by Sylvie Bitton-Giebel from Institut-JU. So we are going to have an overlook at Work Package 2, which title is Study of Damages Due to Impact. First of all, the objectives of Work Package 2 are of number of 6 different objectives. First of all, the idea was to compile a synthesis document on historical incidents and accidents on vessels by impact based on public data and industrial operational experience. Then we wanted to carry out experimental campaigns of impact on vessels to determine damage characteristics induced by impact in terms of type, volume, and so on, to identify correlation between impact parameters and induced damage, to identify the impact conditions that produce immediate failure, and at last, to select the most relevant impact conditions from impact matrix to be further tested in work package 3. And in work package 3, we study the residual performance of the tank, of the impacted tanks. In terms of technical objectives, we have 4 different items. First, to define the study borders in terms of impact energy related to immediate failure. Then we performed impact on various composite pressure vessels, various impact conditions and various vessels. To provide in-depth characterization of impact damage and feed a dedicated database on damage characteristics in relation with impact parameters, and to benchmark NDT techniques that have been presented just before and identify the most relevant in order to characterize damages. So all these are the objectives of the work package. How did we answer to the questions? We defined a test matrix, which was already an important challenge, and the test matrix was divided into 2 steps, step 1 and step 2, and step 1 once again was divided into 2 parts. The first part was dedicated to immediate failure of the vessel just after an impact, and the second part was made in order to feed a database with a great number of damages characterized. In order to determine the immediate failure of a vessel during an impact, we had several tests with several vessel loading, 20 bars, 700 bars, 875 bars, and empty vessel also. We had only one kind of projectile, hemispherical, diameter 56 millimeter with a weight of 1.2 kilograms, and we increased the energy of the impact from 1 kilojoule to the failure. I will show some results afterwards. Thanks to the results of this first part, we could define the different energy levels that were interesting to study, 3 kilojoules, 5 kilojoules, and 7 kilojoules. And for each energy level, we used several projectiles with several weights and several shapes. All these impacts have been performed on empty vessels. So we had hemispherical projectile, conical, and flat, and all these with different mass, 1.2 kilograms, 50 kilograms, and 100 kilograms. In that way, we created a large database with many different damages that could be characterized using NDT. The second step of this test matrix was done on 2 different impact conditions, and then we studied the influence of other parameters. Those parameters were impact parameters related to impactor shape. We had already started this study, but we wanted to go further. And repeated impact. I mean, instead of one impact of 3 kilojoules, we made 3 impacts of 1 kilojoule at the same point in order to see if the damage was different or not. That was for impact parameters. On the other hand, we studied the influence of vessel characteristics. The first parameter was the composite thickness. We had a dedicated specific vessel with nominal thickness increased by 20% and by 40% on the standard 36 liter, and we also impacted vessels a large vessel, 250 liters. Then we will study the influence of the impact localization with impact in the dome area, which will be, of course, different. All the other impacts are performed in the middle of the vessel when there is only one impact per vessel, and at different points on the cylindrical port when there are several impacts on the same vessel. And last parameter was the impact revelator. You can see on the left the glass fiber on the vessel which is impacted. So for step 2 and step 1, all together in work package 2, we have planned 164 damages. Yes, we have created by impact 164 damages. How did we create this impact? The first impact setup is a drop tower. So you can see the mass, the impactor, which is either 50 kilograms on the picture in the middle and 100 kilograms on the video. The shape is always the same as usual, 56 millimeters in diameter and hemispherical. And of course, when we increase the height of the drop, we increase the energy of the impact. On the video, you can see an impact. It has just stopped with 5 kilojoules on an empty vessel. That is the first impact setup with a drop tower. The second one is with a pneumatic cannon, and you can see on the video an impact of 5 kilojoules on a vessel of 700 bars, and you can see the pneumatic cannon and the protection all over, and the projectile is just here. So what have we done? What are the first results we can obtain with this? As I said before, the objective is to get the threshold of the immediate failure. We couldn't imagine spending one vessel for one impact just for this study, so on the vessels are several impacts. One line is one vessel, so we have different pressure, 20 bars with nitrogen, 1, 5, 10 kilojoules. Then 700 bars, 1, 5 kilojoule, and so on. So we have studied different level of pressure with nitrogen and different level of impact energy. We observed several phenomena. With 20 bars, 1, 5, 10 kilojoules, then the projectile was embedded. With 700 bars and 1, 5 kilojoules, the picture is here, we had leakage. Then we tried again with another vessel, and we managed to do 2, 4, 5, 6, 7 kilojoules, but we had a pneumatic burst at the end. 20 bars, we managed to do all the impacts from 1, twice 6 to 8 kilojoules. Of course, the damage is visible. We can't miss it during visual inspection. With the empty vessel, we went from 1 to 9 kilojoules by step of 1 kilojoules. You can see here a very light, hardly visible damage due to 1 kilojoules. And at maximum pressure, 875 bars at 6 kilojoules, but after 1, 2, 3, 4, and 5 kilojoules, we had a pneumatic burst. So we have to take care when we use these figures, because the pneumatic burst or the leakage occurs after a great number of impacts. Anyway, what we can see is that when we increase the pressure during the impact, then the impact energy that leads to failure decreases. But as I said before, it's a first result, and we have to take into account that there are several impacts on each vessel. Just to give you an order of magnitude, 1 kilojoule represents a drop of 50 kilograms at a height of 2 meters, which is more or less reasonable, but 10 kilojoules, it's the same mass, 50 kilograms, but at a height of 20 meters, which is quite important. The second kind of preliminary results we got is the influence of the impact conditions on penetration depth. Penetration depth is the depth of the projectile through let's say, more or less, the composite part. All these impacts are done at the same energy, 3 kilojoules, with the same shape of projectile, and we want to study the influence of the mass and the shape. On the pictures, you always have an hemispherical projectile, but the mass, is different, 1.2, 50, and 100 kilograms, and you can see the damage created on the surface of the composite. Sylvie will show the damage inside the composite, but here we can study the damage in the outer surface of the composite. What we notice is that if the energy is constant, we do not have any influence of the projectile mass on the penetration depth. We have 32 millimeters, 28, 31, and it's shown on this graph. You have the projectile mass, 0, 50, and 100, and the penetration depth. More or less, it's around 30 millimeters for this, except for one which has a conical shape, so which can go further inside the composite up to 50 millimeters. Another thing that we can see is for preliminary results in terms of visual inspection, we have several damages with several conditions. So 1 kilojoule empty, we can hardly see anything. 2 kilojoules, if you know where the impact has been done, you can guess there is something here. 3 kilojoules empty, you can really see some things, and 4, you can't miss it. And when the vessel is pressurized, 1 kilojoule, 875 bars, it's, yes, a little easier to see, but not so important. 2 kilojoules and 3 kilojoules is very important here for this vessel. And here you can compare 3 kilojoules empty, 3 kilojoules 875 bars, and 3 kilojoules at 700 bars. That's one of the reasons why we chose 3 kilojoules at 700 bars in WP3. And 1 kilojoule empty because we can miss this damage on visual inspection, and we want to assess if it's the performance are less or not. And then Sylvie will tell you what we have done in order to characterize these damages with NDT techniques. And perhaps we can go to Sylvie's screen.
Sylvie, we can't hear you yet.
Do you hear me?
Yes, it's good. And we see your screen.
Thank you. So I am Sylvie Bittenibel from Institut de Soudure, and I will speak to you about non-destructive testing we've done on this pressure vessel, composite pressure vessel. The objective of this testing was to determine the damage characteristic in terms of type and in terms of shape and size. So for each impact location, we have done some visual inspection, as Noémie showed you just before. We have done internal and external visual inspection. We have done also ultrasonic testing and, if necessary, some tomography one. So on this screen, you can see the results coming from one impact. For example, it's the impact number 5 on this specific vessel. This vessel was used for the study of impact penetrator shape influence. At the top, you have the results of the internal inspection. at the left and the external inspection at the right. And at the bottom, you have the results of the ultrasonic testing inspection. It's a C-scan image. You have on the y-axis the length of the vessel, and the x-axis you have the all around the vessel. Impact number 5, it's a 3 kilojoule energy with an hemispherical projectile, and this C-scan image, it's a representation of the time of flight answer of this vessel. It means that the color represents the depth of the damage into the vessel. So a blue color, it's near the surface. Instead, red color is very deep near the liner. We define with the other partner definition of the damage. We define different type of damage. We have fiber failure, we have matrix failure, we have delamination, and liner deformation. And for each of them, we define a way to characterize them by a length, by a depth, by a surface, or by a volume. And for each of them and for each technique, we built Excel file with all the characteristics of all the damage induced by impact. I will show you some results of 3 different energy. And you can see on this screen for the 36 liters we studied the results of damage created by the 5 kilojoule energy with 700 bar inside, the 1 kilojoule energy empty, and here is the results you see just before with the last example for the 3 kilojoule energy empty. For the 5 kilojoule energy, you can see it's very visible on the external surface of the vessel. For the 1 kilojoule energy, Noemi said before that it was miscible, so we have done some ultrasonic testing, and you can see here on the C-scan that we have damage created around the impact. But on the tomography at the bottom, you cannot see any crack associated. It's not the same for the 5 kilojoule energy. 5 kilojoule energy, you have a very localized damage created inside the vessel due to the inside pressure. You can see it on the bottom on the ultrasonic testing results. And on the tomography at the top, you can see that there is some matrix failure associated to the delamination. This slide is to illustrate you the choice we made for the step 2 of work package 2 and also for the work package 3 of for the next impact and the choice of 1 and 3 kilojoule energy for the next impact. In the step 2, we studied, as Noemi said before, several parameters for the impact, and we choose. I choose to show you some results coming from the study of repeated impact. We wanted to know if there was a difference on the damage created by only one impact, for example, one impact of 3 kilojoules compared to 3 times impact of 1 kilojoule. And we did the same with the energy of 1 kilojoule, 1 time 1 kilojoule compared to 2 times 0.5 kilojoule or 3 times 0.3 kilojoule. I will show you on the next slide the ultrasonic testing results, but the main result is that repeated impact contributes to the induced damage, but the induced damage seems to be more related to impact condition. For example, vessel empty versus vessel at 700 bar than its energy. This is the results, ultrasonic results for this study, where you have on this vessel 3 impact locations with 3 different energy impact repartition. We also studied on this work package the influence of the change of thickness. For now, we don't have all the results, but for now, we have the same behavior on the induced damage when the thickness is changed. We study also the impact of the change or the adding of a revelator layer. We have on the left on the screen the picture of the vessel with the glass fiber, and we can, and on the right, on the left, sorry, the picture with the carbon layer, and we cannot see or barely see the impact location. So the glass fiber is not helpful on this case for the visual testing, but we can see on the ultrasonic testing results that you have still the same behavior on the induced damage, with or without the impact revelator layer. For the conclusion, you have to know that these results are still partial, because we have not yet all the computed tomography results, and we have not yet all the birth results. But the first conclusion are that impact energy leading to immediate failure decrease when pressure in the vessel during impact increase. For a given energy, projectile mass has no significant influence on damage. For low energy, the elimination is observed through the composite thickness regardless of the thickness. Pressure in the vessel during impact seems to have a significant influence on the damage. And for the work package 3, we choose in this work package 2 impact conditions, 1 kilojoule empty and 3 kilojoule with 700 bar. And this work package 2, we began to build a database to provide inputs regarding this work package 3 modeling. Thank you. I will let Michal speak to you now for the work package 3, and I want to remind you the possibility you have to chat with us and ask your question. Philippe?
Hello everyone, my name is Michał Barcikowski and I am from Wrocław University of Science and Technology. I will talk about the outcomes of an still ongoing work package 3, which is concerned with residual performance assessment of impacted tanks. I will present here tasks 3.1 and 3.2. After me, task 3.3 will be presented by Kasper Lassen from NTNU. There are four main objectives of work package 3. The first objective is to quantify residual burst resistance of impacted tanks, to determine failure mode, and to compare it with the burst resistance of healthy tanks. This will be achieved by gradual pressurizing the vessel to monitor damage evolution with acoustic emission. The final assessment will be the residual burst pressure of a vessel. The second objective of the task is to assess long-term influence of impact on tank performance. This will be achieved by exposing the vessels to fatigue load, more precisely to pressure cycling. And this fatigue load will be interspersed with acoustic emission monitoring of the evolution of damage. The third objective is to adapt existing numerical models or develop new ones to predict the influence of well-known impact effects on composite tank performance and on their safety. And the final objective is to identify the most critical impact conditions with respect to operational safety of composite pressure vessels. To assess the short-term residual performance, the impacted vessels first go for the NTT characterization to assess the initial state of damage. Then the NDT is mostly visual inspection and ultrasonic testing. After the inspection, the vessel is pressurized while monitoring the acoustic emission, following which the vessel is once again pressurized, this time until the burst is achieved. To assess the long-term residual performance, initial steps are the same as for short-term assessment. Impact followed by NDT characterization. Then the vessel undergoes the long-term performance test campaign. Finally, the residual performance after the campaign may be found by burst test. Alternatively, we may perform computed tomography upon the vessel to see if the damage evolved during cycling. As Sylvie has said before, two impact conditions were selected in work package 2. 1 kJ impact on empty vessel and 3 kJ impact on a vessel pressurized to 700 bars with nitrogen. Some additional impacts were performed at other impact conditions, namely at elevated energies up to 700 kJ on both empty and pressurized vessels. In each case, the vessel is impacted perpendicularly in the middle of the cylindrical section, and the vessel is impacted only once. The striking part of the impactor has hemispherical shape with the diameter of 56 millimeters. Acoustic emission is performed on 36-liter vessels using 8 acoustic emission sensors. 6 of them are placed on the cylindrical section of the vessel, and 1 sensor is placed on each dome, as you may see on the picture I show you. Larger vessels require more sensors, up to 20 sensors in case of 225-liter vessels. For the acoustic emission test, the vessel is pressurized according to a distinct pressure profile, as you may see in the picture. The maximum pressure for 36-liter vessels is 1050 bars. This pressure is equal to test pressure of this tank design. This pressure is reached through several increments with 5 to 20-minute holds at each increment. The acoustic emission is gathered both during holds and when the pressure is increased or decreased. In a long-term testing campaign, the cycling is interspersed with acoustic emission tests according to the profile I have just shown you. Acoustic emission test is performed after the impact and then after each cycling step. There are 3 cycling steps: 50 cycles, 5,000 cycles, and another 10,000 cycles. In each cycle, the pressure is increased from 20 to 875 bars and back to 20 bars. The cycling rate does not exceed 10 cycles per minute. The total number of 15,000 cycles was chosen so that it reflects 3 times the number of cycles in predicted lifetime of the vessels. And now for the results. I show you here examples of acoustic emission signatures of a healthy vessel and vessels after 1 and 3 kilojoule impacts. You may see that the signatures are quite similar to each other. There is no indication that these vessels are in any danger of rapid damage progression, even at test pressure, and thus they will be perfectly safe for short-term usage. Here you may see the burst pressure of the vessels together with impact points on vessel surface. Please note that the surface damage is barely visible, especially in the case of 1 kilojoule impact. In line with the acoustic emission results, we do not see any drop in burst pressure of impacted 36-liter tanks compared to healthy ones. Please recognize that the confidence intervals overlap, and in all cases the burst pressure is higher than the minimum burst pressure, which for this design is 1575 bars. This means that the short-term performance of the vessel was not significantly influenced by these energies of impact. Still greater energies would be needed to compromise the performance of the vessel, which I show you in the next slide. Here you may see burst pressure for vessels impacted once with given energy up to more than 9 kilojoules. The vessels are impacted either empty or pressurized to 700 bars. It is obvious that sufficiently energetic impact does indeed decrease the burst pressure of a vessel. It may be seen that the pressurized vessel loses performance at higher impact energies than empty vessels. Pressurized vessels are stiffer and therefore seem to alleviate the severity of damage. The line for pressurized vessel is currently based on just 2 points, but we plan to improve this with more impact points to put more points on the graph. You may also note that there is a distinct plateau for pressurized vessel where impacts up to 3 kilojoules do not seem to lead to reduction of burst pressure. A similar thing may be also true for vessels impacted while empty, only in that case the threshold of performance reduction would lie around 1 kilojoule. For the long-term performance, the vessels are still undergoing the long-term performance campaign, so we do not have definite results yet. However, we may compare the evolution of acoustic signature for healthy vessels and vessels impacted with 1 kilojoule up to 5,000 cycles. One thing to note is that the vessels are quieter after a large number of cycles than when they are relatively new. That said, there is not much sign of damage evolution in impacted tanks, indicating that they would be safe for use. To conclude the results of these 2 tasks concerned with residual performance of impacted vessels, it has to be stressed that the short-term performance of 36-liter vessels does not seem to be significantly impaired after 1 kilojoule and 3 kilojoule impacts. The threshold for the loss of short-term performance lies at higher energies. Also, no loss of performance in the long term is expected either after such impacts, at least up to vessel's predicted lifetime. It is worth noting that according to current standards, impacts are performed at energies lower than those in our tests. It might be therefore worthwhile to consider if the impact conditions should not perhaps be correlated to the working pressure and volume, or in other words, to the wall thickness of the vessel. All these results we have gathered here will be fed into the numerical model, which will now be described by my colleague Kaspar Lassen from NTNU, which I now give voice to.
Kaspar, we can't hear you.
Do you hear me now?
Yes, thanks.
Okay, I will try to show my screen. Is it working?
Yes, it works.
All right. Thank you, Michael. Good afternoon. My name is Kaspar Lassen, and I'm calling you from NTNU, Norway, to briefly summarize our work on numerical modeling of composite over pressure vessels and a little bit of experimental work connected to it. The objective of the modeling is to predict the residual burst strength after mechanical damage. So that includes both the short-term residual burst pressure under quasi-static conditions and the long-term residual lifetime under cyclic pressure. Before going to the numerical models, a few words about the context regarding the damage. As you all know, the damage is typically modeled as a consequence of a physical event, which includes parameters such as impact energy, shape of the impactor, boundary conditions, etc. However, if a cylinder is inspected, for example, in a filling station, this knowledge will not be available. Only the information which can be collected with non-destructive test methods will be available. So all in all, our models can do both. They can model the creation of the damage from a physical event, but also we have a possibility to implement damage from non-destructive tests. So this last point actually points to the importance of the quality and the resolution of the NDT methods. For example, on the right we see an impact detection or location detection from a grid of inwound optical fibers. And also what is important is information transfer from non-destructive testing to the numerical models. To facilitate this, we have developed what we can call a code of how we share this information between the partners. Essentially, it consists of simplified damage geometries and for different failure mechanisms. And this was also shown previously by Sylvie in work package 2. So to address the two objectives, two models have been implemented. First, the short-term burst model, where the impact damage can be incorporated. It can show the damage development. It can predict the residual burst pressure. However, proper input of material parameters is critical, just as critical as the model itself, or for that matter, proper input of damage sizes and types. In addition, fatigue model has been implemented also in three-dimensional finite element analysis. The fatigue life there is calculated for failure mechanisms in each of the elements. Failure mechanisms, two of them, fiber tensile failure and elimination, are considered. The failure is predicted. Thereafter, elastic property is reduced. That results in stress redistribution. So this describes the one loop The model was first developed for simple geometries, and currently the implementation to cylindrical shapes is in progress. So a little bit more detail about our short-term model. The short-term analysis is conducted by a 3D parametric model, which has been implemented in Abacus Explicit. On the right, we see an overview of the components, and the model includes the following options. We can have an arbitrary composite layup. We can have an arbitrary impact location in the cylindrical section. We can have impact on empty or pressurized pressure vessels. We can have no impact, where we prescribe the damage from non-destructive tests. And we have options of various boundary conditions, for example, neck mounting or belt locking on the ground, or whatever custom conditions we desire. And of course, various impactor shapes such as hemispherical, conical, cylindrical, etc. The results from the short-term model have been compared to a few of the results from our small-scale vessels that we have wound in-house in NTNU. However, the quantitative calibration with Hypactor results is still in progress, as the experimental data is now available from the other partners in the Hypactor project. So this slide explains the principles for modeling the fatigue behavior. The model employs two failure mechanisms, fiber tensile failure and delamination. And the approach is based on the fatigue curves, and the failure criteria is the minor sum, which is evaluated separately for each of the elements in the selected region of the model. The principle of the one analysis loop is shown to the right of the screen. This fatigue modeling approach has been implemented on tensile specimens with central hole or symmetrical notches, where the results have displayed expected results of monotonic growth of damage and damage surrounding the areas where we have stress concentrations. The fatigue modeling approach will be applied on the same geometrical framework as is used in the short-term model. With modeling, there always comes a question about input parameters. The typical test methods for materials are defined for flat panels, whereas cylinders are produced by filament winding, and therefore it is assumed that this material has different properties than flat panels. The critical parameters for our modeling were identified as fiber tensile strength and toughness, and also interlaminar shear. And we have developed a few test methods, including our own small-scale pressure vessels, to characterize short-term and long-term response. So to address delamination, we have developed a method which evaluates through thickness shear properties which control the delamination behavior. And to our knowledge, this is the first study for curved short beam shear and digital image correlation. On the left side, you see the experiments, and on the right, corresponding numerical models. To obtain the fiber tensile strength properties, we have developed a small-scale vessel design shown on the lower part of the slide. And this is a simple construction consisting of inexpensive and reusable parts, and it allows to load these small-scale vessels in uniaxial tension also to do the regular burst testing. And we are also experimenting with winding in optical fibers. So to conclude this small presentation, modeling involves many challenges. Some of them are noted here, for example, how to define the impact damage and how to get all material parameters and how to ensure the quality of the model. We have created a short-term analysis model and a fatigue analysis model using three-dimensional finite element analysis, and the work on the latter one is still ongoing. All in all, the technology has been developed, however, there are still a few programming challenges. And last but not least, most interesting parts are ahead, that is the comparison to Hypactor experiments, as the data from other work packages regarding the residual performance and non-destructive testing is now available. And also the experiments have pinpointed a few of the phenomena which need to be reasoned and investigated by modeling. Thank you for your attention.
Hello, can you hear me?
No, we don't.
Hello, can you hear me?
Yes, now we can hear you.
Okay, perfect.
Okay.
Can you see my screen?
Yes, yes,
Okay,
we can see your screen.
okay, great. So, good morning and good afternoon, everybody. Welcome to the Work Package 5 presentation. Work Package 5 is, let's say, dealing with the conclusions of the Hypactor project and dissemination of the results and recommendation to codes and standards. My name is Patrick Poyer. I'm from Hexagon Lincoln. If you look at the objectives of this work package, as mentioned, it's about dissemination of the results. So it's first of all the scientific knowledge about the tests and simulations, NDT methods we are gaining through the course of the project. Maybe also revised methodology for design and qualification of new composite cylinders, as well as new or revised methods for periodic inspection and testing. And finally, the recommendations of the outcome into international codes and standards. Therefore, this work package was divided into 5 different tasks. First task was creating the external communication tools. The second task was the dissemination of the knowledge and expert feedback. Third task was recommendation for periodic inspections. Fourth task, recommendation for qualification testing. And the last, as mentioned, recommendation in existing and new regulation codes and standards. One or the other of you may have already visited the Hypactor webpage. This is the key and the most important external communication tool for us. So here you can find further information about the project participants and structures, but also, and I think that's more interesting for everybody, the results will be published on this webpage as well. You can find already some public deliverables, more to come within the next 3 to maybe 6 months. And also, if we have interesting publications from the participants, we will share this and link this onto the web page. Like you can see here on the screen, it's a publication from Caspar, who just presented to you the simulation part of the project about the sensitivity of the burst performance of impact pressure vessels to material strength properties. So that's already a result coming out of the Hypactor project, what you can find on this web page. And here you will find also in the future new results and also new information what's going on towards the end of the project. Dissemination of knowledge and expert feedback was and will be done due to international publications and presentations at conferences or through journal publications. We have created an action plan to disseminate the results, so we have discussed internally where and how we can disseminate the results, mainly concentrated on the NDT methodologies, the cylinder qualification and the periodic inspections. For that we created an expert networking group, and you all that are now listening to the webinar are part of this group, where we want to have the exchange and the advices for our ongoing work, and basically start the exchange of information with you on this topic. We have already participated on several events, conferences the past years. They are basically spread around Europe, from Germany over Poland to Spain, and this will be continued within the next year. It's probably going to be till the mid of next year, where we will be able to participate on several seminars, conferences. One important activity will be the final Hypactor workshop, which will be in the second quarter of 2017. The location is still TBD, but of course you will get information as soon as available about the location and the date of the workshop. And of course you can see and follow the updates on the website to get this latest updates on this event. There we expect to have then basically all the recommendations and results gathered in the final workshop. And also the plan is to update and bring this table to the web page, so you can meet and greet us on the different conferences where you want to participate. The next task, as mentioned before, is regarding periodic inspections. We are analyzing and describing different methods of periodic inspections in the Work Package 3 and Work Package 4. And once we have finalized the analysis and also the study of these different methods, we then will formulate the suggestions for EN ISO standards for future revisions and improvements of the periodic inspections. Just as an example, you probably know what are currently used periodic inspections. For example, for metal pressure vessels, you normally do the hydrostatic proof test plus external and internal inspections. For CPVs, there's, for example, an ISO 11623 standard which describes the periodic inspection and testing of CPVs, compact pressure vessels, where you, for example, have different acceptance criteria, damage levels that are defined mostly by, let's say, external measurements of the depth of the damage or the abrasion or whatever kind of external influence the cylinder has seen. And for CPVs, we have seen that external visual inspection may be not sufficient, because you may have damages inside of the composite that you actually don't see with superficial inspections. Similar topic is the qualification testing. Also here we are doing a lot of different test methods, a lot of different energy levels. these are described as mentioned before by my colleagues in Work Package 2 and Work Package 3. And here we will also do our studies and discussions and see what we can propose as maybe improvements of existing ISO standards with regard to qualification testing. Also here some examples you may know. For example, the drop test on the left side, which is basically used as a standard in, for example, the EC79 or other ISO or European qualification standards, where you have different drops, 4 different drops in different orientations with a minimum energy level of 488 joule, and you do then afterwards a cycle test to see whether you have any degradation or not. On the right side, there's an example out of a new standard in development where you actually don't do the impact with the cylinder itself, but by an external impactor, where you have a certain dimension of the impactor and then different location where you hit the tank with the impactor. So I think in a nutshell we also have some interesting results coming out of the impact testing we are doing. So there might be a way to have alternative impact test modes and energy levels that we can recommend coming out of this this project. Last but not least, there is a working group 24 within the ISO TC58 subcommittee 3, which is dealing in general with a safe design of composite cylinders, and Hexagon as well as Air Liquide. Hexagon is the convener, or provides a convener for that working group, so we have very good inputs of the topics of ongoing and maybe also future work items that can be addressed in this working group. And furthermore, as mentioned before, Hexagon as well as Air Liquide are members of several other working groups within EN and ISO, so we can make sure that results coming out of this project will be exchanged with the experts of the DIN ISO working groups. At this point in time, I think that's all to Work Package 5. Definitely more coming at the end of the workshop and at the end of the project in the final workshop, when we have formulated the final recommendations out of the Hypactor workshop. As mentioned again before, the website where you can find all the information. I assume also this presentations or the video of this webinar will be posted on this webpage. So for everybody who wants to have a second view on the presentation or the film or the webinar, you are able to see this at a later point in time. I think that's all so far from the different work packages, and we are opening for question and answer session, I guess.
Okay, Fabien speaking. Do you hear me?
Yes, we can hear you.
Okay, so Fabien, so as Patrick said, the question and answer station is open.
Okay.
So feel free to ask any questions. We already get some?
Yes, there is a first question from Pietro Moreto. So some questions related to the recommendation for RCS on impact energies as mentioned in Work Package 3. Hypactor advice is to adjust impact test energies according to the NWP, volumes and thickness to be able to discern between robust and non-robust design. So the question, will the recommendations be a detailed document accompanied by a table of values for the thickness, volume and WP relationship with the impact response? And there is a second question, but I let you answer to this first.
Okay, I can take first and can try to answer. We got for the moment maybe a partial answer to that question. This is clearly our aim to provide some recommendation on how to assess the robustness of a vessel or robustness of design of composite vessel with respect to impact. So we expect that we will be able to provide some more understanding about the relation between impact and loss of performance of cylinders submitted to impact. So yes, some first elements could be to provide some tables about differences on how to assess different cylinders, but it's not sure yet. What we should say first is all the results that we present and all the results that will be gathered within the Hypactor project are, at least we can say for the moment, specific for the cylinders that we tested. That means it's a cylinder designed and manufactured by only one tank manufacturer using the same materials, same resin, same fiber, or same family of fiber. So it's a little bit too early right now to say that these results could be extrapolated directly to any kind of design, any kind of materials, any kinds of architectures. It's a little bit early, but yes, one of the first recommendations that we could provide, we will try to provide some results from our database, of course, to support some evolution of the standard. We will also try to provide some maybe evolution of the impact testing configuration, taking into account the specificity of composite cylinder exposed to impact. That is maybe, as you have seen in the presentation, maybe adjust the energy level, but also adjust the location, the number of impact, and the state of pressurization of the vessel, maybe. But it's a little bit early to conclude right now. I think we still need to finish the trial that we plan in the Hypactor project, compare between all the different designs, the service pressure, the length of the diameter ratio of the different cylinders, and assess if the conclusion, the preliminary conclusion that we were able to draw are effectively validated on all these different designs. And then we will be able to provide some recommendation with respect to this design. First element. I don't know if anybody want to add anything to the question, but okay. Of course, our main aim is to provide some recommendation, at least. It would be even to confirm some the relevancy of the actual testing conditions that are used, or even to propose some evolution or some further research to validate some new testing configuration. Okay.
Yeah, you just answered to the first part of the question. I think you can see on your screen, Fabien, the follow-up of that question. So the second part of the question is, it's not clear to me what is the definition of robust. Is robust acceptable? In other words, is it here suggested to use the results to assist design, so not for type approval of the vessels?
Okay, I can start at least, but any team member can also complement. Feel free. My personal thinking, at least, is that first, of course, we want to increase our understanding of the sensitivity of the composite cylinder exposed to mechanical impact. So understand if this is something which is accessible, let's say, with only one type of impact in one location or very few locations in one pressurization state. If we think, considering our technical result in the project, that the actual testing configuration are not discriminant or capable of distinguishing the let's say most performance design against the some design that could be very sensitive to impact, then we will be able to provide maybe some proposal for having this testing configuration to be adjusted. And then, of course, it is also into our mind to develop the modeling capacities to be able to extrapolate results between the different technical cases that we tested in our experimental campaign, but trying to be able to predict the residual performance of a cylinder that has been impacted, knowing the damage by NDT characterization. But also, if we can, develop some specific criteria, maybe try also to implement in the, let's say, design office, the design culture, or the design rules, include also some specific criteria that will enable the designers, the composite designer, to test not only the composite architecture with respect to burst pressure, but also impact resistance. Okay, if we go
and
to the next one, if anybody.
Yeah, the third part of the question is, so you said the impact test values of the present standards have much lower energies than tested here. So the question is, those values aim at guaranteeing operative performance in very specific real case of impacts. Which are the typical real-life situations for the values adopted by Hypactor?
In Hypactor, we.
Oh, okay. I will just make a few words, and then I will get the microphone to Pierre Blanc-Vanet from Air Liquide. We get the first state-of-the-art study from Air Liquide and Hexagon at the beginning of the project to get some feedback from the testing field, let's say, about what they think a vessel is likely to face in service. So, of course, we started from that point. But also, as Noemi presented you before, we were also interested in the way to assess what could be the limitation of the visual inspection, particularly for transportable cylinders that are visually inspected prior to filling. It is also important that we know if a damage that is not or very barely visible from the external point of view have an influence on the integrity of the cylinder. So, of course, here we saw that, at least from the preliminary results we have, that the 1 kilojoule, which is, as you said, a little bit higher than the values that are for the moment implemented in the current standards, we think that the 1 kilojoule energy is an energy level that is very interesting to assess. But not only. This is for some of the justification about what we think the 1 kilojoule is interested. And then I will leave the microphone to Pierre for some complement. Maybe also Hexagon will want to complement on that topic.
Yeah, thanks, Fabien. One thing that is important to understand in Hypactor project is that we focused on the behavior of the cylinder when it is impacted, not so much about what kind of real-life situation can lead to such energies, but what happens, what can the cylinder endure? Because then, instead of just testing one level of energy and saying it's good or it's not good, then we can give information about what the cylinder is capable to withstand, and that information can then be used for usage purposes. For example, if you're a car manufacturer and you want to simulate a crash test, then you are able to say what is the energy that is transmitted to the cylinder, and if you know what is the behavior of the cylinder in that kind of energy range, then you can determine if this is sure, or if you need additional things, or if you need to change your design. So the fact that the level of energy applied in the qualification should represent a real accident and not the critical damage for the tank, maybe that is, and in the qualification you need that level of energy. But for inspection purpose, you need to know if you have a cylinder that has been impacted and you don't know the event, you need to know is it still good or not. So that's why we focused it on that angle. We took the subject with that angle. But in the final recommendations, I think we'll separate both cases, getting information on the cylinder and ensuring a minimum level of safety, which could be independent of thickness and everything, just depend on how the cylinder is used.
It's one of the tricky part of the job. The impact is very difficult to define, because you could face in service always different impacts. The fact is we focus on the project not on the impact generation, because when we will recover the cylinder at the filling station, then we don't know what kind of impact generated the damage, but we want to, with proper NDT techniques, characterize the damage and being able to deduce or predict if we can still keep the vessel in service, or if we have to provide further inspection, or if we have to reject it from service. One example maybe which can be in the middle of the value of energy that we present today is maybe the case of a forklift that impact a bundle of cylinder or a cylinder. That could be an energy level which is in the middle of the 1 to 3 kilojoule impact, for example, depending on the type of forklift used, the speed, its weight, and things like that. Okay, I think we have a question maybe for Feti from Institut Soudure about the number of sensors used for the 255 liters. That is higher than the number of sensors used for the 513 liter. Feti, maybe?
Yes, I'm here. So the question was why we used 18 sensor for the 500 liter and 20 sensor for the 255 liter. So the answer is too simple. Due to the sensor placement is performed according to the attenuation curves, and in the 255 we have the attenuation is more important than the 513 due to the thickness. So the thickness is 3 times higher in the 255 than the vessel 500, and also the length of the 255 is longer than the 500. That's why we have more sensor. So for example, for the 255 we used 18 sensor in the cylinder part with the 3 sensor per circumference, and for the 500 we have 4 sensor per circumference because the diameter is more important. That's all.
Okay, thank you, Feti. Another question, where is located the failure of healthy vessels, and for the impacted vessels, static and cycling? Are these locations failures repeatable? Noemi?
Yes, okay. When the vessel is...
Do you hear us? Is it fine?
Yes, we can.
When a vessel is impacted and we carry out a burst test, each time the failure starts at the impacted point. It's repeatable, there's no surprise. The only surprise that can occur is when the vessel is impacted several times and at the same energy, and then it's quite hard to guess where will be the start of the burst phenomenon.
And for the healthy vessel, maybe Hexagon want to complement, but we have a good assessment provided by Hexagon on the repeatability of their cylinders due to on the burst behavior. Even if you have some scattering of the burst pressure, of course, due mainly to the carbon fiber distribution of performance, but also maybe its process. We have a quite good and repeatable location of the failure and propagation mode. And as Noemi said, as for the impacted cylinders, we make, let's say, a critical defect compared to the other state of the cylinder. The burst is always starting from one of the impacted points.
Okay, Patrick, do you want to comment it, or do you think the answer was fine?
I think the answer was fine, yes.
Okay, thanks. Next question. How do you define immediate failure when impacting an unloaded cylinder in a meaningful way to get direct comparison to impact on loaded vessel?
Okay, of course it's a good question. We think of it also. There will always be some differences between these different impact on various pressure, because you don't have the same energy inside the tank that could act as a driver force for the burst to occur. But when we are impacted the empty vessels, we perform some video endoscopy, so with a camera inspecting the internal surface of the liner, of the boss liner junction. We are seeking for any sign of break, cracks, or failure mechanism which could have gone through the liner or the boss section. When we are making a single impact on the cylinder, then of course the cylinder is characterized by NDT, but then it will be also repressurized after, at least to check its integrity, but also to go for residual performance assessment by burst pressure, for example, or for cycling. And if we can't go through up to the pressure that we find that we need, of course we will identify a leakage. So the immediate failure for the empty vessel could be either a leakage that we show during a repressurization. That could be directly after impact, something that we see that has ruined the integrity of the liner, or that could also be directly penetration of the impactor through the thickness of the composite and through the thickness of the liner. Okay?
Okay, so next question is, did you discuss the possibility of impact out the cylindrical part? Mirai tanks achieve a very good gravimetric density also by thinning the part joining dome and cylindrical parts. I am not an expert, but I could imagine that this could have a negative consequence on impact resistance.
Okay, very interesting question also. Let's say for starting, I think all the people around the table or the computer, let's say, know that there is not much information outside on the open literature with respect to high pressure composite vessel subjected to mechanical impact. So one of the first main objective of the Hypactor project is to generate for the first time a wide database that will aggregate the results of the characteristic of the impact, the induced characteristics, the characteristics of the induced damage, and then the corresponding residual integrity of the cylinder, or loss of performance if you prefer. Of course, for the beginning, it's easier either to perform the impact and to assess it, or even to be able to run multiple impact on the one cylinder to impact the cylindrical part, of course. More often, when you design cylinders, you design the cylindrical part a little bit weaker than the dome region also. So, okay, we first tested and focused on the cylindrical part to start from, let's say, the more repeatable part and the most simple part, let's say. But of course, as Noemi said, we also aim at investigating how it behaves on the dome subjected to impact. So we have planned, but not performed yet, to run some impact directly into the dome area at different location points. But what we could say is we can guess that this area of the cylinder is a part which is very, very specific and variable between the different kind of cylinders. There could be a very big variation of thicknesses depending on the design, and the location of the thinnest part of the composite is not always the same depending on the design. So we will hit the dome also. We know from the actual the current testing also in the standard that this dome triggers a very specific and maybe in sometimes some critical behavior of the vessel. So it is of very it's a major importance to investigate how it behaves in the dome. Okay. So we will surely also investigate the dome and try to provide some information about the dome behavior. But I would say that it will be even more specific to the design you tested. So maybe we will be also due to provide some very specific configuration testing or maybe adjustment on the cylinder testing.
Question for Michel.
Okay, thank you. Then we have 3 more questions for a few more minutes. So the first is about acoustic emissions. Acoustic emission results shown are based on global or zonal analysis. How do you use acoustic emission location results to determine a pertinent criteria? Michel?
Maybe Feti, perhaps, for the signal treatment?
Yes, so we show just zonal analysis of for the study of the evaluation of dispersion, but to build criteria, we will base our analysis on both zonal and location analysis at the same approach as followed by the French guidelines, so as the Appendix 7. So we will base our criteria on these 2 methods, zonal and location. Okay.
Okay. Thank you, Feti. Then we have another question. How many fiber staus must rupture at a given point in the cylindrical section of the vessel that was modeled in order for the burst pressure to be reduced according to the modeling? So, Andreas, I let you answer.
Yeah, this is Andreas Echtermeier from NTNU. Basically, we use a slightly different approach. We look at the damage that we get from the impactors, and then we put in a certain area describing this damage. So let's say if we find that fiber failure has happened over 1 square centimeter and 2 millimeter depths, we put that into the FE analysis, and then we calculate the effect of it on the residual strength or on the remaining fatigue life. So basically we put in the size of the fiber damage and then can calculate the effect of it. We haven't gone the other way to show how many fibers are needed to have any effect. But I think you can imagine if you have a very thick laminate and you break only a few fibers, it will not do much. And if you have a thin laminate and you break many fibers, the effect will be very dramatic. So that's obvious. But we basically have the FE calculation capability to calculate this question. And so if one wants to do it directly, then we would have to look for a certain layout and dimension of the pressure vessels, and then go and start deleting a few toes, which would mean a certain area of or volume of damage, and then we can calculate the effect of it.
But I suppose it's also very variable, because it depends where, depending on the stress ratio you have on the layer that you want to cut some fiber bundles to. It's very depending on the design and where you want to cut these fibers, so it's difficult to answer.
Yeah, that's right. I mean, you tend to have the fibers more highly stressed in the inside than on the outside, so that makes a difference as well.
Okay, maybe a question for Patrick about the design lifetime of the cylinders.
Patrick? Yes.
Yes. Can you hear me? Yeah. The question is whether there's a finite lifetime for the vessel design, or, for example, 20 years. So basically, the lifetime is determined many times by the regulation code and standard which is applicable. So, for example, for the 36-liter tank, it's certified according EC79, which limits the lifetime to 20 years. Other cylinders used in this project are, for example, PED certified, which enable longer lifetimes, but at least have 20 years lifetime as well. I think that's all.
Okay. I think it's time to conclude. I think we get through the main question. I hope we provide clear answers. Feel free to contact us after the webinar. To get my email on the first slide, you will get our contact of all the team members from the website. You have also the email from Philippe that organized the webinar. So feel free to contact us, and I remind you that we are not at the end of our project. We will have still something like 6 months to go, and we will perform a final workshop at the end of the project to try to disseminate most of our results, to get things advanced about these impact tolerance of composite pressure vessel exposed to impact, mechanical impacts. So I seize the occasion to thank you for your attention during this webinar, and looking to reading from you or getting in touch with all of you. Thank you very much. Have a nice afternoon or end of morning for the people who join us from the US. That's all for my part. Thank you very much, and looking forward to reading or seeing you later. Thank you very much, and keep in touch from the Hypactor website. Thank you very much.